All right, so what we're going to talk about today is what happens after translation. And that's called post-translation modification. This happens after translation. It's the word post.
Does this go with
Yeah. It's just next. Now, the thing is, in translation, we make what's this symbol right here stand for? The primary sequence of our protein, which is what this is. What amino acids are in there? What order are they in? That's what translation does for us. Translation puts the right amino acids in the right order. But this is still not a protein because it hadn't been what yet? What hadn't happened to this sequence yet? It needs to join with another polypeptide, and more importantly, it needs to what? Fold and bend into the right way. Shape. That's what happens in post-translation modification. Several polypeptides get together, and they fold and they bend into the right shape. If it's a protein that's going to stay in the cell that made it, it's not getting, what's the word for getting sent out? What's the word for when a cell makes stuff and sends it out? Maybe excrete, but usually we don't use that word. Usually we use secrete, or what's the word for the process of sending it out? Exocytosis. Okay? If it's a protein that's not going to be secreted, if it's a protein that the cell made for itself, that little primary sequence of amino acids is going to go into this little tunnel-like structure called the chaperonin. So this little protein sequence, let's say this is my chaperonin. He's going to go in here. Maybe another one's going to go in there. And what's going to happen inside the little tunnel? That's where they're going to mix and bend and fold and twist. Is in the chaperonin. They'll come out of what? Yeah, in polypeptide chains, out a protein. So the chaperonin is the tube, the tunnel, where they get together and they fold, where polypeptide chains get together, fold and bend and twist into the right shape. Now, on the other hand, if it's a protein that's going to get shipped out, secreted, it's going to go into the rough ER, right? And in the rough ER and in the Golgi, that's where it's going to twist and bend and get modified. And then eventually, it's going to get shipped out. Exocytosis. Yes? It's where polypeptides get with other polypeptides and then they fold together into the right shape. Into a protein. Chaperone. For proteins getting shipped out of the cell, though, that happens in the rough ER and in the Golgi body. But if it's a protein that's going to stay in the cell that made it, all that folding and twisting happens inside a little tube called the chaperonin. It's right there. Chaperone. Nope, it's not chaperone. All right, now this stuff we've already kind of talked about, but I want to add a little bit to what we've already talked about here with DNA. We know that prokaryotes don't have introns, right? No introns. Therefore, they don't have to do what to their mRNA? Yeah, if you don't have introns, you don't really need to process your RNA, right? Your primary transcript goes straight to the ribosomes and it gets translated. Well, here's the thing. Lately, the last few years, scientists have figured out ways to put eukaryotic DNA into bacteria, to use them like factories to make stuff for us. But could I take a gene straight out of me and put it into a bacteria?
No.
It wouldn't know how to deal with what?
The mRNA.
No,
the bacteria wouldn't know how to deal with what part of my DNA? What did I just mention? Introns. They don't know how to deal with introns. It doesn't have spliceosomes or any of that stuff. They don't have them. Probably the best example of what I'm about to talk about is insulin, human insulin. We know diabetics need a constant supply there, right?
Yes.
Insulin is a protein, which means it's coded for by DNA, a gene, a specific gene sequence. Scientists found that gene sequence in humans. We know what the gene for human insulin is. We know how ATGC, that sequence. But could we cut that sequence straight out of a human chromosome and put it straight into a bacterial chromosome? No, because they don't have the processing stuff to deal with it. So before they put it into the bacteria, scientists had to figure out a way to get out the introns first. And here's what they found. Eventually, they located a processed piece of mRNA, the insulin mRNA. So it's processed insulin mRNA. The piece of mRNA that had the code for insulin. But what had already happened to that piece of mRNA? The introns were already taken out. Exons spliced back together. Well, they still needed to do a little bit more with it because they couldn't put mRNA into the bacteria either. They need a piece of DNA. So some guy was thinking when he did this. He took this mRNA and he treated it with reverse transcriptase. What do we know reverse transcriptase does to RNA? Takes it back to DNA. But since this was already processed RNA, what kind of DNA did it turn it into? DNA without flex, without the introns. We call that kind of DNA cDNA. DNA without the introns. Eukaryotic DNA minus the introns. That piece of DNA they could then put into the bacteria, and they did. Today, diabetics who take insulin are taking insulin that's been grown in bacteria. And they grow the bacteria in big room-sized vats like this, liquid-filled vats. Why use bacteria to do this? Yeah, bacteria can reproduce in just a few minutes, right? And every minute, every time they reproduce, what do they do to that human insulin gene? They pass it on. Okay? So that in a day or two, if you started with just a handful of these bacteria with the human insulin gene in them, after a day or two, you got millions, maybe billions. And what are they all chugging out? They're all chugging out insulin. So the human insulin that diabetics take today, it's human insulin made by bacteria using human genes. They're using the human gene. Mm-hmm.
So if my sister has it, she has diabetes,
Mm-hmm.
does that mean that kids are going to have it?
Not necessarily. It tends to run in families, but it's not one of those things that if your mother has it, you're going to get it kind of things.
Neither of my parents have it.
Yeah. Not even then. It's not always that way. It's what's called a complex genetic trait. It's not one of those that if you got one gene, you're going to get it kind of thing. It's more complicated than that. Anyway, key thing. If you want to put eukaryotic DNA into a bacteria, you've got to get DNA without the introns because they don't know how to do that. And the best way to do it is find the proper RNA that's already been processed, treat it with reverse transcriptase, and get this cDNA stuff. Eukaryotic DNA without the introns. That can go into the bacteria. What do we call that when we put bacteria from one thing into something else and change it? Well, we spent 2 days talking about this just a week or two ago. Take DNA from one thing, put it into something else, and change it. What's that called? A transformation. A transformation. So we transform these usually they're E. coli, the bacteria we use, usually E. coli, and change them into E. coli that make human insulin, which is a good thing for us.
Why is it usually in E. coli?
Because E. coli is the most common bacteria in your body. It's usually not harmful, although there is a strand of E. coli that can make you sick. Most E. coli is not, and we know a lot about it. So that's why we do it.
Is there anything else like the diabetic insulin that they do this with?
No, not as far as I know. They could use other bacteria, but I think they usually use E. coli.
No, but I mean, like, is there anything else where people put DNA?
Other than insulin.
Yeah.
Yeah, we can use bacteria to make any protein that you can make. So, for example, these guys, all these athletes that are taking human growth hormone, that's made this way. Steroids, made this way. Any human proteins or human products that we want to have extra of, we can put the genes or gene for that substance in a bacteria and they'll start making it.
What if I wanted to continue growth hormone to get taller?
My brother does those, so you would
It's
just.
very expensive. Unless your insurance is paying for it, you're probably not gonna be able to afford it unless you got a major league football salary coming to you.
My brother,
NFL's football
he
salary.
uses human growth hormones to make him taller, so he goes to Nashville every year. He has to take shots every day.
He's not really short though, is he?
I mean, he was. He's not anymore. He's not high.
Right. I want some of that.
Right. Yeah, I mean, it works. Like I said, it is expensive. The doctors are not supposed to subscribe it to you unless you have a problem, unless you're really short for your age.
Really, really small.
Yeah. Yeah.
So what if-
They'll do that in that case.
What would happen if you gave it to like a midget?
Nothing.
I
Oh,
can't,
maybe
okay.
not a midget.
My brother used to take them to make them grow, but my neighbor across the street, she used to take them to like make her stop growing because she got too, like, she got too big.
And you think they were taking the same thing?
She had to take shots for it.
I don't know about that. My guess is they were taking something different. Probably wouldn't have been human growth hormone, because human growth hormone
But what would they
is going to make you grow.
How would
So it will make you grow.
I don't think it would. Maybe they're taking something to keep her from getting off human growth hormone. 'Cause, I mean, we all make human growth hormone, right? We all make it in our pituitary gland or our hypothalamus, and from there, we make different amounts in different parts of our lives. That's why at puberty, we tend to make a whole lot of it. And other parts of our lives, not so much. If you take growth hormone after your growth plates are hardened, your bones get thicker, your muscles will get thicker, and you'll start to look funny. That's why Barry Bonds, the baseball player, he looked like a normal black guy back when he started playing baseball back in the 80s. Today he has this huge head. His forehead is real thick and it sticks out. His jaw is really wide, it protrudes. His cheekbones are really big and they stick out. He doesn't look like a normal black guy.
Can we see him?
I'll try to find a picture of him in a minute when I finish recording. His bones got really, really thick and he got really, really strong. Okay? Probably not from just growth hormone. He's probably taking steroids and all kinds of other stuff. But he went from being a good baseball player to being the best. Because he was juiced up. I mean, he was good to begin with. But he went to being better than Babe Ruth there for a while because of all the drugs that he was taking. Yeah.
You know who Charlie and Melissa Walker are?
Go ahead, I missed you there. Second.
Do you know who Charlie and Melissa Walker are?
Oh.
They go to school. My little sister's best friends with their little sister and their little brother.
Mhm.
And their little sister Catherine is 12 years old, and
Yeah.
she was 400 pounds and 7 ounces.
Right.
And you look at her and she's 12 years old, but she looks like she's 5.
Yeah, she's really
She's really short. And then Dominic just turned 8, and he looks like he's 6.
Is it a genetic condition or was it just because they were premature?
I mean, like, they were both born premature at, like, under 2 pounds, so can that, like, affect your whole entire life?
I'd have to know more about the situation to really answer that. I don't know.
But I heard that people that are born prematurely, like, very premature, are usually smaller than this.
Yeah, they typically are. They typically are, but there's more to it than just that probably. Yeah. Listen, guys. Uh-huh.
Like they had, I guess they, I don't know the story. I remember hearing primordial dwarfism or something like that. Is that genetic?
Most forms of dwarfism are genetic, yes.
And like there was one guy who was like 40 years old and he was about 10.
Yeah, there's all kinds of weird forms of dwarfism. There's lots of different kinds. Austin, you got a question?
Okay, so like my mom is like the shortest person in the family. Not the shortest person, but like she I'll say she's like okay, she's like average height, like 6'1". Like,
That's not average.
okay, that's tall.
For-
In our family, it's average.
For a woman, your mom's that tall?
Yeah.
That's not average for a woman. That's tall for a woman. I don't think she's 6'1".
Okay. She's taller than me.
Right.
Taller than me. Next subject. And my dad is like short and like real stocky, like. So would that like if I took human growth hormone, would that be going against the grain a little bit?
Now, if you, I mean, at your age right now, if you took human growth hormone, you would grow. Yeah. Now, if I took human growth hormone, I'm not going to get any taller. I'm going to get thicker. Yes. Listen, please.
Well, used to be a neighbor. She had twins, and they were premature about 2.5 months. So I know premature, like Andrew was saying about it might affect you the rest of your life, but also why does having a twin, even if they're full term, sometimes keep them smaller than they might have been if they were single?
One might take the nutrients from the other one.
Yeah, in most situations, I don't think it does. And I don't know that that's true. Because I'm thinking of lots of different twins I know, and they're all normal size.
They're greedy, they're like this.
Yeah. Well, usually they're born small, but eventually they usually catch up. All right, guys, we got to move along here. I'll get some more questions in a minute. Mutations. A mutation is any change in your DNA, right? Any change in your DNA. Any change in the sequences of your DNA. Turns out there's a lot of different kinds of mutations. We're going to talk about maybe 3 or 4 that you need to know. The first one, I'm going to go back to the genetic code table for a minute so I can show you something. If we take our sequence of DNA over here on the board, and let's say that this piece of DNA right now, that is CGC, let's say this mutated so that this C, the CGC, the last C there, instead of it being a C, let's say it mutated and that became a T. So just one letter change. Well, if the DNA changed by one letter, what else is going to change by one letter? mRNA. So here this was supposed to be CGG, now it's going to be GCA. Well, now let's look in the genetic code table. It was supposed to be GCG, which coded for alanine. Now it's GCA. Let's look GCA up. GCA. That's still alanine. Is that going to cause any problems, that particular mutation? Nope, because we still get the same way. Same amino acid, which means same protein, polypeptide, which means same trait. Nothing happens. That kind of mutation, where a base changes, but it doesn't really cause any problems, it's called a silent mutation. Silent mutation. Silent point mutation in particular. The point means only one what is getting changed. One nitrogenous base. A point mutation is when one codon, one single nitrogenous base is changed. That one would have zero effect because you still get the same amino acid. And that's the good thing about our DNA. We have several codons for the same amino acid. So sometimes, even if you're wrong, you're still right. Okay? There's some room for error built into your DNA. Now let's look at a different situation. Yep. This time, now remember, this was supposed to be this was CGC up here. So that was supposed to be a G. So this time, let's say that instead of this last letter mutating, let's say this first one did. CGC, let's say this C became an A. Let's make it be an A. So if this became an A, that means this is now going to be a U. Now if we backtrack to our genetic code table. Now remember, our original codon was supposed to code for alanine. But now we've got UCG. So UCG right here, we get serine, a completely different amino acid, which probably means a completely different protein, which ultimately means a completely different trait. And that's usually not a good thing, right? That kind of mutation is also called a point mutation, but it's called a missense point mutation. Missense. Meaning, what's miss mean? Like mistake. You did something wrong. You get the wrong amino acid.
But that doesn't change too much, right? Like that's not like
Well, it depends. It depends on what gene it happens in. It can be really bad. people who have sickle cell anemia, they have this kind of mutation. Just one little nucleotide is wrong in their DNA, and that causes their red blood cells to be shaped the wrong way, and that can lead to death. Okay? Just that one little letter wrong in all of their DNA. So that's a missense mutation. That one little change causes one amino acid to be changed, which can end up causing weird things to happen. Yeah. It could lead to cancer, depending on what kind of gene it happens in. Now, another kind of point mutation is called the nonsense point mutation. And that happens when there's a mutation somewhere in the middle of the DNA chain, and instead of coding for an amino acid, the codon becomes what? A stop. So the code mutates so that it becomes a stop code instead of an amino acid code. So you start making your protein, and then all of a sudden, right in the middle of the chain, it just stops. So you don't get the protein at all. Typically, what's that going to lead to? That kind of mutation, what's it typically going to lead to? Usually death of that cell. Usually that cell's not going to make it, because it's usually going to completely be missing that whole protein that it needs. And if it's an important protein, it doesn't have it. And so it dies most of the time.
That's in there to be called Mongolism.
Yes. Mongolism.
I was just yeah, further Mongolian idiot.
All right, now here's the thing. Silent point mutations have no effect. One letter changes, but you still get the same amino acid. Missense point mutations, one letter changes. That changes the amino acid that you get, which ends up changing the trait most of the time. Nonsense point mutations, a normal codon becomes a stop codon. And that causes that protein really not to get made at all. Those are really bad typically.
Why are they good?
Because you're missing a whole protein that you're supposed to have.
How do you know?
It's amazing that there's as many opportunities for things to go wrong, and that as many of us turn out to be pretty normal as we do. Okay? Because there's a lot of places where things can go bad.
So it doesn't happen just like for a day that you get the wrong coded protein. It happens for your entire life.
No, and I'm going to get into how it happens. Most of the time, this is just happening in random cells in your body. Those cells usually just die.
That's just random time, so it's not really like a lifelong.
Right. We're about to get into when it could be a lifelong thing in just a second. Yes.
So like on the nonsense mutations,
Well, not necessarily, because most of the time they're both going to die. The nonsense mutation is actually usually more severe than the missense one. Because with the missense one, you get a similar protein at least. With the nonsense one, you just don't get the protein at all. That's usually really bad. Now, this kind of mutation that I'm about to talk about is even worse. It's called a frame shift mutation. Frame shift mutation. And there's two versions of this. Let's say that this was our DNA, TAC, AGC, GCC, ATT. And let's say that something was happening during replication, and this C right here just got left out. It got deleted. So now instead of reading TAC like it was supposed to, it's going to read TAA. And instead of reading AGC, it's going to read GCG. And instead of reading GCC, it's going to read CACCA. You see why it's called a frame shift mutation? It's changing the reading frame. All the words change, right? Which means every what changes? Every amino acid from the point of the mutation on is going to be different.
So
Can that be good? No. That's almost always going to lead to the death of that particular cell.
So
Yes.
you can have a normal cell for the first couple years of your life functioning normally. What causes it to just all of a sudden change?
Sometimes it's just a random mistake during replication. It can be things like radiation, chemicals you're exposed to, cigarette smoke. That can lead to cancer. These kinds of mutations typically are going to lead to death of the cell or cancer. Now, that what we just looked at is called a deletion. We left off a nucleotide. But it would be just as bad if instead of taking off that, let's see, what did we take off? We took off a C. Instead of taking off that C, let's say just a random nucleotide got added, like a G. Just as bad, right? Because now we read TAC, that amino acid ends up the right one. But now instead of AGC, now we end up with GAG. And instead of GCC, we're going to end up with GCG. So every amino acid past the mutation is going to be the wrong one because we shifted the frame. Up here, it shows you that in like regular English words. 3-letter words. Our whole sentence is made out of 3-letter words. Here, we inserted one letter, an O. And when we inserted that O, that changed the whole meaning of the sentence, right? It made it garbage. Down here, same thing, except we deleted, what did we delete? We deleted an I. And when we deleted that I, everything from that point on is wrong. So frame shift mutations are either insertions or deletions. And either way, those are really serious mutations because they change everything from that point on. One more thing I want to show you, and I think this will be the last slide in this PowerPoint. Where the mutation happens is really important. Where it happens. An important word for today is this word right here, somatic. What are your body's somatic cells? They're your non-sex cells, your normal cells. They have nothing to do with sex, like your red blood cells, your skin cells, your muscle cells, your brain cells. If you have a mutation in a normal somatic cell, are you going to pass that on to your children?
No.
No. The only mutations that you can pass on are mutations that happen where? In your sex cells. Unless it happens there, you're not going to pass it on. Typically, if a mutation happens in a somatic cell, either that cell dies or it becomes cancerous. But if a mutation happens in a gamete, is that going to affect you?
No.
Not going to affect you, but it is going to affect your children if that particular gamete happens to get fertilized, right?
Genetic mutations only passed on from mother.
No, can be passed on either way. Give you a good example. My sister's little boy, you guys all probably know he has a genetic form of cancer, right? Okay? Okay? He has a genetic form of cancer. Neither of his parents have that gene. Neither one of them have it. So apparently what happened, either in the sperm that made him or in the egg that made him, we don't know which, there was a mutation, a gamete mutation. And that gamete made the initial cell. What's the initial cell called? When you get sperm and egg together, what do you get? Zygote. So his zygote had a mutation in it. What does that mean about every cell in his body? They all have that mutation. He's got that genetic cancer mutation in every cell in his body. Now, when he has children eventually, what does that mean? There's a good chance he can pass that on to them, even though neither one of his parents had it. Neither one of his parents have that gene. Just he got unlucky, and the sperm or the egg that made him had a mutation in it.
What are the possibilities of that happening?
It's fairly common.
So will it keep reoccurring his whole life? Or?
It's possible. There's always a threat that it's going to come back. They treated it the first time, and he's okay right now. Cancer seems to be gone in remission. But because of that gene that's in his body, it could pop back. You never know. Key thing, mutations that are somatic cell mutations, they're going to affect you and you alone. Mutations that happen in a gamete are what we call a germ cell. That's a new word today too, germ cell. We'll see that more here in a minute. Start over on that. Germ cell, just like it sounds. Your germ cells are found either in your ovaries, if you're a woman, or your testes if you're a guy. They're the only cells in your body capable of doing what kind of cell division? Meiosis. Yep. Only cells in your body that can do meiosis, which means they're the cells that eventually form your what? What does meiosis make?
Sex cells?
Sex cells. Okay? So the germ cells are the diploid cells in your body that can do meiosis. The only cells in your body that can do meiosis. What do we know about the number of germ cells that you ladies have?
But they have a limited number.
You're born, actually even before you're born, your germ cells start dying out. And by the time you get to 50, 45, or 50, they're gone. And we call that menopause. Okay? Us guys, on the other hand, our germ cells can not only do meiosis, they can also do mitosis, which means we're constantly revamping ours. We're making new ones every day. So we never run out. Okay? Even as a 90-year-old guy still has germ cells.
I think it's
Still making them.
So like,
Still making them.
and women like run out of their germ cells like early? Is that how some people aren't fertile?
Typically not. Usually women who are having fertility problems, it's usually more related to their uterus. If there's something wrong with their uterus's ability to hold the baby.
What about early onset?
I don't know a whole lot about that. It can happen, I know, but I don't know a lot about it.
Is early onset menopause being caused from women where their cycles like every week or every other week instead of every month?
If a woman was having that, then yes, that would be a problem. Because eventually you're going to run out of eggs.
Wouldn't that person also be really pale?
Probably. But back to what I'm saying up here. Hey, somatic cell mutations. Could they be important for evolution? Somatic cell mutations. No, because they're not what? They're not passed on. The mutations that lead to evolution are the germ cell or the gamete mutations. Let's say you go to the tanning bed and you're sitting back in the tanning bed and all those UV rays are zapping your skin cells, and one of your skin cells, the DNA inside that skin cell mutates. That's a somatic cell mutation. In that skin cell, it might become cancerous, or maybe you just killed that skin cell.
What is it called when it's just yeah, what are your freckles? Like your freckles or your moles from tanning beds, that's not...
Can be. Well, a lot of times the freckle is just a clump of skin pigment.
No, but when somebody tans too much, they get like a mole-looking thing.
Like a liver spot?
It's like cause it can lead to cancer.
Okay, so what?
I'm not sure where you're going with that. I'm not sure. Yeah. Guys, what? No, not usually. No, not usually.
But they can become,
Sometimes they can, depending on the situation. All right, let me stop here for a minute.